Common feature in many mathematical models is the presence of a parameter along with the variables. So parameters are quantities that do not depend on the independent variable, but that assume different values depending on the specifics of the situation. So for example, the Malthusian model of population growth said dp dt equals k times p. So it says that the rate of growth is proportional to the size of the population. But that constant of proportionality varies. It can change depending on what population you're studying, right? Like fruit flies are going to have a different constant of proportionality than humans, right? So that constant of proportionality is what we're going to study today. We're going to study the effect of these parameters, how they change the solutions to a differential equation as you vary the parameter. It can be a really important question when you're studying real-world phenomenon. Okay, so I've got a whole family of differential equations here. My parameter is mu. So my independent variable is y. Sorry, my independent variable is t, my dependent variable is y, and mu is just some parameter that we're going to play with and see how it changes the solution to the differential equation. So we're just going to look at the parabolas that are given by the right-hand side of that differential equation, y squared minus 4y plus mu. So f sub 0, that just means put in a 0 for the mu, so we just have y squared minus 4y. So we're looking at one particular member of this family of differential equations. If you make mu 0, we have a differential equation dy dt equals y squared minus 4y. So I've got a graph of that parabola. So remember, this is a graph of the derivative, right? So let's label the horizontal axis, right? So this horizontal axis is y. And this vertical axis right now is dy dt, right? This is a graph of the derivative. And then this particular parabola is f sub 0, right? That is the member of the family when we make mu 0. So I want to draw a phase line that corresponds to this graph. Remember, this is a graph of the derivative. So I'm going to draw a phase line. Where are my equilibrium points? 0 and 4. Okay. To the left of 0, the derivative is positive, right? So when I'm less than 0, this derivative is above the x-axis, it's positive, so that means I'm pointing up. Between 0 and 4, this parabola lies below the x-axis, it's all negative, so my arrow and the phase line points down. So because my derivative is negative, that means the solution is going to be decreasing. And then after 4, positive, so my arrow points up. So there's my phase line. So as I change mu, if I put in different mu's instead of 0, if I put in 1 or 2 or 5, how is that going to change this parabola? Shift it up or down. Yeah, so these are just vertical shifts that we're going to consider. Okay, so we're looking for what's called a bifurcation value. We're looking for a specific mu where the quality of the solutions change. Okay, where instead of having 2 equilibrium points with up, down, up for the arrows, we're looking for some qualitative change. Doesn't really matter where those equilibrium solutions are, but we're looking for something different than 2, right?
So that would be where the cross the x-axis.
Yes, if you lift this parabola up high enough, there's going to be a moment, there's going to be a specific mu where there's no longer 2 solutions and there's only 1, right? And then when you pass that point, there's going to be none. Okay? So the bifurcation value is that specific mu where my vertex is going to land on the x-axis. So we're looking for that mu. So what value of mu gives this parabola? 2. No, 4. Yeah. Right? Because we have to shift up 4. Right? Oh, yeah, it's different. Yeah, you have to read the scale on the axis. Yeah, so 4, you have to shift up 4 to get there. So in this case, we can visually figure out what mu is pretty easily, but sometimes when the equations are more complicated, we have to do some analysis with algebra. So in this case, I can just rattle off mu is 4 is that special point where the quality of the solutions changes. But if that wasn't obvious to you, you would say, okay, well, what has to be true about both the function f, what has to be true about the parabola, and what has to be true about its derivative? So in order to get this point on the x-axis, right, I need the function to equal 0. Right? I need to know where the function equals 0, and I need the derivative to be 0 at that point. So both things have to happen simultaneously, that the function is 0 and the derivative is 0 at the same time. So I would solve f mu equals 0 and f mu prime equals 0. Solve those two equations simultaneously, substitution, elimination, whatever, because you're going to have two variables, y and mu. So I'm just going to work through it real quick so that we can see it done out. Y squared minus 4y. And then the derivative of that is 2y minus 4 equals 0. So you have two variables, two unknowns, y and mu. You want to find the mu that makes both of those things true.
So solve the derivative.
Yep. Solve the derivative and then plug it back in. So here we get y is 2. Plug that in over here. 2 squared minus 4 times 2 plus mu equals 0. So that's 4 minus 8, negative 4 plus mu equals 0. And you get mu equals 4, which is what we saw visually. All right, so let's choose two nice numbers, one a little bit bigger than b. B is our special value of mu. We call it the bifurcation value. So in this case, b is 4, right? So b is 4. So one a little bit bigger and one a little bit smaller. Let's go with, nice integers so we don't have to do too much crazy arithmetic. We'll go 5 and 3. So on the same axes that we were drawing before with the f sub 0, I want to graph 3 more parabolas, f sub 4, f sub 5, and f sub 3. So I want to make mu 3, 4, and 5 and graph those parabolas. So I'm going back over here. So when mu is 4, right, I know that I hit right there. And we have a parabola that goes like this. That's f sub 4. That would be y squared minus 4y plus 4. When mu is 5, that means I would take this f sub 0, this is the original f sub 0, and shift up 5 units. So that would land me like right here. And I've got this green parabola. Intersecting what? Yeah, I guess yeah, this one should have gone through 5. The y-intercept of that should be 5, right? So I guess I didn't draw it very carefully. There we go. All right, and then f sub 3, that means take your original f sub 0 and shift up 3. So it's going to go to like right here. And then I do care where the x-intercepts are because that's going to tell me where my equilibrium points are. So if I have y squared minus 4y plus 3, where does that equal 0? You can use a quadratic formula. This one actually does factor. This is y minus 3 times y minus 1. So it's going to have zeros at 3 and 1. And the y-intercept of this one is going to be 3. There we go. And this is F3. All right, so all I did was sketch some more parabolas here for different values of mu. I sketched the specific special value of mu, which is 4, because that's where you can see as you shift these up, we go from 2 equilibrium points, then they get closer together, but still qualitatively the same graph. But then all of a sudden they sort of merge into 1 point, and then there's no more equilibrium points. Okay, so we're going to sketch something called the bifurcation diagram. So a bifurcation diagram has mu as its horizontal axis. So we're going to sketch phase lines for all the different mu's. So this is y is the vertical axis. And for all my different mu's, I'm going to sketch a phase line. So for mu equals 0, we already did a phase line, right? I sketched it over here. So my equilibrium points were at 0 and 4, and it went up, down, up. Okay, so I'm going to draw that one first at mu equals 0. So that's this guy right here. Mu equals 0. Equilibrium points at 0 and at 4, and it went up, down, up. And then I also have specific information for 3, 4, and 5. Those are the graphs I drew. So I'm going to put a vertical line at mu equals 3. And it had equilibrium points at 1 and 3. And it also goes up, down, up. And then at 4, I can draw my phase line because I have a parabola that I can follow. It has just one equilibrium point where? At 2. Yeah, let's just go back and verify on the graph. Yep, this pink graph is F sub 4. It has its equilibrium point at 2, when y is 2. So I'll put an equilibrium point on there. And then how should I put in the arrows? Up, up. Yeah, because on both sides of that equilibrium point, the graph is positive above the x-axis. Up, up. Okay. And then at 5, I've got a phase line. I can draw a phase line. There are no equilibrium points, so I don't put any dots on. But what should I put for arrows? Up, because it's always above the x-axis. So I just put an up. So this is the start of a bifurcation diagram. Okay. It just shows you how the solutions change qualitatively as you change the parameter mu. Yep. Yes. Yes, this only works for autonomous differential equations. Because it relies on the fact that we can write all the information about the solutions in a phase line. Yeah. All right, so now we're gonna look at these phase lines, and they set the pattern for all the other phase lines. So we're gonna add some more lines to our bifurcation diagram that alternate with the lines we have. And then we're drawing some arrows and dots. And then you connect your equilibrium points with a nice smooth curve, and you have a bifurcation diagram. So these set the pattern. So I kind of know what's going to happen from all my other phase lines. If I wanted to draw one at 2, I would know that the equilibrium points are going to be closer together because they are far apart here, and then they get closer together until they become 1. So I can put these in, sort of estimating. These are going to be like, I don't know, here and here and here and here, something like that. And then I could put another one over here and they're going to be further apart. I could put more over here, but there's not going to be any. They're just all going to be phase lines with an up arrow. And then you can connect your equilibrium points and you get sort of a parabola looking thing. And it's not really a coincidence that it looks like a parabola and that's what our differential equations looked like. Yeah, you'll need to you'll need to draw a few, like you'll need to capture all the qualitatively different phase lines. Like, okay, I've got 2 and then I've got 1 and then I've got none, and then you can fill in the blanks by looking at the pattern. So this is what's called a bifurcation diagram. All right, so the last thing is that now I can draw solutions, right? So it's really, it is really difficult to keep track of what all the different graphs that we're drawing are representing, right? So the first graph that we drew were the parabolas. These were graphs of the derivative, right? Based on the dependent variable y. So these were graphs of the derivative. Then I used those graphs of the derivative to draw phase lines to create a bifurcation diagram. Right, so these are phase lines that all represent different solutions for different mu's. And then you can use those phase lines to draw solutions of the graphs t, y, right? The actual y of t functions that solve the differential equations. So this one, this b minus, that was the one a little bit smaller than the bifurcation value. Bifurcation value is 4. A little bit bigger, 5. Okay, so when I used f sub 3, right, the equilibrium points were at 1 and at 3. So I could sketch the phase line again if I need to remind myself. 1, 3, and it was up, down, up, right? Okay, so I put in equilibrium solutions at 1 and at 3. And then I'm just going to put in at least one graph in any region above, below, or between equilibrium solutions. So there are lots of solutions depending on the initial condition. So just pick a random initial condition. Like I'm going to pick y of 0 is -2. So down here below my 1, there's an up arrow on my phase line, which means the graph is always increasing. So it probably looks something like this. And if I pick an initial condition between my 2 equilibrium points, my phase line says that this graph is always decreasing because of the down arrow. So it probably looks something like this. I'm just choosing random points in between and on either side of the equilibrium solutions. And then if I pick an initial condition larger than 3, this arrow is pointing up, so this is always increasing from left to right. And then for the 4, that was my special value where there's only one equilibrium solution at 2. So draw in the equilibrium solution. And then the arrows were both up. So this must look something like pick a random initial condition that's below the equilibrium, and it's going to have to increase up towards it. And then an equilibrium solution above, and it's always increasing, so it looks something like that. And then over here, there were no equilibrium solutions. when we used mu equals 5, and the arrow was always up. So if you pick a random initial condition, all you know is that this function is always increasing. You don't really know anything about its concavity or how fast it's increasing. So you might draw it like this, right? You might just draw a line. All we know is qualitatively it's always increasing. All right, so quick thing before we move on. This equilibrium solution at 3, right here, sink or a source? Source, yeah. Because the solutions, as you go from left to right, the solutions are leaving it, right? And you can see it in the phase line because the arrows are pointing away. This pink line beneath it, sink or source? Sink, the solutions are heading towards it. And in the phase line, the arrows are both pointing towards it. What about this one? Node. Because one's going away and one's going towards. All right, so that's it for the demo. You can either go back to the activities you were just working on, or if you were done with those, jump into these activities.